Good morning, students. Welcome to Complex Analysis live lectures. In this class, we will discuss about winding number of a meromorphic function, Rouches theorem, and its applications. And we also give second proof for fundamental theorem of algebra using Rouches theorem. Okay. Fine. Now, what is meant by to understand what is meant by winding number? First, start with definition of what is meant by f. A function is said to be meromorphic. So, a function f is said to be meromorphic if, so this is said to be meromorphic if it is analytic except at some points where those points are precisely poles. Okay. So, suppose assume that it is not analytic at some points. If those points are singularities, and particularly those singularities should be poles. So, a function is said to be meromorphic if at all it has only poles. Okay. Then we can say that it is meromorphic. So, any analytic function we can call it as a meromorphic. We won't call that function as meromorphic if at all it has a singularity which is not a pole. That means if at all it is a removable singularity, or if it is a essential singularity, then that function is not a meromorphic function. Okay. So, meromorphic function means analytic except at possible exceptions are poles. Okay, fine. Now, to understand what is meant by a winding number, so consider the meromorphic function f in a domain. Okay, then interior to positively oriented simple closed contour C. So if this is our C, okay, in interior, this inside this C, f is meromorphic. That means wherever it is not analytic, those points are poles for that function. Okay, and that is analytic and non-zero on C. So on C it is analytic and it is non-zero. Okay. Then, so here it is a Z plane. Okay, and here it is a W plane. So our W is equal to f of Z, right? Then what we consider the image, we will call it this as, so whatever we are having here, this we will call it as gamma. This is nothing but image of this C, okay, under this function f, that W is equal to f of Z. So under this transformation, call it this as gamma. So this is our gamma, okay, which is image of this C. You can check that it need not, even though this is simple, this gamma need not be simple. So this gamma need not be simple. Okay. So if you have Z, then Z is mapping to this, Z is mapping to this W. So let's take some other color. Okay. So if you move this one around this one, so this will move here. Okay. So it is not necessary that whatever direction this C has, under this transformation, this gamma will have same direction, but definitely it will have either clockwise direction or anti-clockwise direction. One direction this will have gamma. Okay. Then one can observe that because this f is analytic at non-zero on C, that means f of Z here, f of Z is not equal to 0 for all Z belongs to this curve C. Okay. So because f of Z is not equal to 0 and our W is equal to f of Z, that means if you combine these two, this one and this one, what we will get here is W is not equal to 0. Okay. That means this curve, whatever we are getting this gamma, it doesn't passes through origin. Okay. So this gamma does not pass through origin. Okay. That I have written here in this small text, but I don't want to read this one, so I am explaining. Okay. Fine. Then now take W naught, this is the point, okay, and W, this W naught is a fixed point, and W we will try to move around this curve gamma. Okay. That means when we move, when you start from this Z naught and here, and if you reach this again Z naught, this W also start from W naught and it should reach this W naught. Okay, under this image, right? Okay. So take this W naught in this W plane, okay, which is fixed, which is a fixed point, and call it phi naught, the value of argument of this W naught. Okay, we know argument of any complex number takes infinitely many values. Then take this W starting from W naught. Okay, so we will rotate, I mean, we will go through this entire curve gamma starting from W, and we will reach again W naught. Okay, so if we traverse, so traverse W starting from W naught, okay, then reach this W naught again. Okay, at that time, when whatever we reach here, whatever argument of this W, when it reaches W naught, okay, this we will call it as phi 1. Okay, because this is also one of the value of, so you can write this phi 1 is also one of the value of this phi naught only. So we have started from here phi naught, W naught, then we have traversed along this path gamma. Okay, so however it is there, then you reach this W naught again. That value, whatever we are going to get, that we are argument of that, we are calling it as phi 1. Okay, so therefore obviously phi 1 minus phi 2, phi 1 minus phi naught, sorry, phi 1 minus phi naught is nothing but change in argument of this W. Okay, but our W is f of z. Okay, so our W is f of z means this phi 1 minus phi naught is nothing but the change in argument of this f of z when we traverse this z starting from z naught and reaches once. Okay, so that is the idea. Therefore, so we can write, since this W is equal to f of z and argument of this phi 1 minus phi naught is the change in argument of W, this implies what we get is phi 1 minus phi naught is nothing but change in argument of f of z, that we will denote this by, so we will denote this by that we will call it as this change delta, and along the path C, and this is delta C argument of f of z. This delta C just to denote the change when you revolve around this C, when you traverse around this path C. Okay, that is our phi 1 minus phi naught, right? But because phi 1 and phi naught and phi 1, they are arguments. Okay, that means it is just like some angle theta plus 2n pi. Okay, their difference, we can check that it is an integer, right? How we can see that? Since this phi 1, okay, minus phi naught, this is nothing but capital argument of this W naught. Okay, that is our vector where we started. Then say suppose 2n1 pi. Okay, then minus phi naught, which is argument of same W naught, okay, which is principal argument, then again some 2n2 pi, that you can check that this is same as argument, principal argument will get cancelled. This is simply 2 times n1, okay, minus n2 into pi, right, or 2 pi times, we can write 2 pi times n1 minus n2. So therefore if you put this n1 minus n2, so 1 by 2 pi times this delta C argument of f of z, which is equal to n1 minus n2. This is an integer because n1 is an integer, n2 is an integer. So this we will get it as an integer. And whatever we are getting to this one is called the winding number. Okay. So what is this winding number? We will, you start from any point. So you take from z0 and you traverse this along with this curve, okay, and take its image, okay, under the map W is equal to f of z, and W0 at when you have started, what is its argument, and when you traverse entire curve and reach again W0, whatever we have got the argument, that difference, which is nothing but the change, okay, that we will denote this by 1 by 2 times of 2 pi times this one is nothing but n1 minus n2, which is an integer. This is called, we will call it this as this winding number. Okay, winding number of, when we consider this curve of the curve gamma around this origin. This is origin. Okay, right? So we can observe that what is meant by winding number is like how many times it is revolving around that curve the moment it starts from z naught and reaches to this z naught again. Okay, so we are basically taking starting from z naught in this z plane, and we are revolving here, and the moment we reach again z naught, how many times it is like uh, go around the origin, that we will call it as a winding number. If it goes in some other negative direction, then it will be minus. If it goes in a positive direction, it is plus, right? So that's why it is called winding number. That means like how many times it revolves around the origin, that is nothing but the winding number, right? And we'll I hope this is clear. Okay. We can observe that if, because it is, we are talking about how many times it rounds around origin. So if this doesn't revolve around origin, then winding number is obviously 0. Okay, that means if at all it is not at all rotating around the origin, then the winding number is 0. That is because the change whatever we are going to get is not your argument value will change if there is a complete rotation of 2 pi. Okay, so if that happens only if our curve is rotating around that origin. Okay, that means if it doesn't involve origin when it is rotating, then we can see that winding number is 0. Okay, this same point of discussion we did when we discussed about log. Okay, elementary functions log. What can we talk about? Their multi-valued functions, how multi-valued functions formed and so on. Okay, fine. So if that curve doesn't revolve around origin, that is obviously a single valued function. It is similar to here, right? Fine. Now it is not possible to find what is this n1 minus n2. Okay, so what we will do is we will try to give the formula for winding number using what is called argument principle. Okay, so we will see what is meant by argument principle. So what it says is that suppose you take C, which denotes a positively oriented simple closed contour, and assume that this f of z is meromorphic in the domain interior to C. Okay, that means possibly what are allowed are poles are allowed. Okay, and f of z is analytic and non-zero on the curve C. Okay, with counting multiplicity, suppose if z is the number of zeros. Okay, with counting multiplicity, that means if it is repeated, that also we will count, and p is nothing but number of poles, of course, of f of z, and they are inside C. Okay, then this winding number is nothing but, so this winding number is nothing but z minus p, number of this difference between number of zeros and number of poles. Okay, that is the winding number. And while proving this proof, we also give explicit formula for calculating winding number in terms of integration. Okay, because in some textbooks, the winding number itself they will define what is meant by in terms of winding number in terms of integration. Okay, so in this here, winding number is if we know how many zeros it has and how many poles we have for that given function, then winding number is difference of those. Okay, fine. So how we'll prove this? The idea is we'll show that this winding number is nothing but winding number. We will also show that this is actually is nothing but 1 by 2 pi I times integration of f dash of z upon f of z dz over C. Okay, this we will try to prove this. Okay. So the idea is we will try to evaluate this integral. Okay, and one side we will get this difference of argument, and the other side we get z minus p, so that they are equal. Okay. So we will evaluate this integration of C f dash of z upon f of z in two different ways. Okay, one using parametrization, the other way using Cauchy residue. That means because this f of z has poles, so we can apply Cauchy residue theorem to evaluate integration. right? So the first one is very simple. Takes z is equal to z of t, and t is the parameterization from a to b. Okay. Then simply simplify this. I don't want to write that. F dash of z by f of z is nothing but f dash of z of t into z dash of t by f of z of t dt, where t is from a to b. Okay. Now, because this w f is non-zero on c, therefore w is not equal to 0 on gamma, right? So this f of w, which is equal to f of z, is non-zero. Okay. This here we should write as a gamma. This f of z is non-zero on c. We can write it in an polar form. So any w we can write it in polar form. That means this f of z of t, which is rho of t into e power phi of t, where t is from a to b, and substitute those values here. That means what can you say about if this is, then what is f dash of z of t, then z dash of t. Okay, it is basic calculation which I don't need to spend more time. Then simply substitute integration of c f dash of z by f of z dz by putting this differentiation value. What we get here is this, because this is by fundamental theorem of calculus for real variable calculus. This is nothing but natural logarithm of rho of t from a to b, and this is I times phi of t from a to b. Okay, when you substitute limits, what we will get is natural logarithm of rho of b minus natural logarithm of rho of a plus I times rho of b minus rho of a. Okay, and remember this rho. Okay, what we have here is the constant radius. What will change is only angle will change, right? When you rotate through that curve, only radius will be there. So because at a and b where you start, okay, and once they reach there, the radius doesn't change. If at all it changes is only argument value, right? So therefore what we know here is rho of b is same as this rho of a, because where you started, you have traversed and reached to that point again. Okay, so from origin the distance is same. That's why rho of b is equal to rho of a, and phi of b minus phi of a, which is phi of a is the starting argument, then after reaching again phi of b. Okay, that is the change in argument that we know. This is nothing but delta c times argument of f of z. Okay, that winding number, right? So if you substitute those two values here, what we'll get is integration of this, in this integration value is I times, because this I is coming here, I times delta c into argument of f of z. Okay, or other words, this delta c, our winding number is 1 by our winding number is, here we have defined 1 by 2 pi times delta c into argument of f of z. So 1 by 2 pi times delta c of argument of f of z. From here what we'll get is, here we want to divide both sides, multiply by 1 by 2 pi and bring this I here. So what we'll get is 1 by 2 pi I times f dash of z upon f of z dz over c. So while calculating one way, we got, this is our formula for winding number. How we can find the winding number using this. Okay. Now what we do is, because this f has, it is meromorphic, it has some zeros and poles. Okay, so we will calculate this integral using residue theorem. Okay, so as I said, f dash of z by f of z is analytic inside and on c, except the points inside c at which the zeros and poles of f occurs. Okay, because we are considering f dash of z by f of z. So for this new function, if you want, you can call it this g of z. Okay, whether g is analytic, where g is not analytic, wherever f has zeros, at that places g is not analytic, and also where g is not analytic, wherever f dash of z does not exist. Okay, so f dash of z does not exist, that means singularities happen. Okay, so this function f dash of z upon f of z, it is analytic except at zeros and poles of this f of z. Okay, so g of z is not analytic wherever f of z has zeros. Okay, and g of z is not differentiable wherever f dash of z is not defined, right? That is the reason f dash of z upon f of z, this is analytic except at zeros and poles of f of z. Okay, fine. So we can apply residue theorem for to calculate that integration of g of z, which is integration of f dash of z by f of z, right? Now we'll see what if something is a 0 and if something is a pole, what values we get, right? Suppose assume that this f of z has a 0 of order m naught at z naught. Then we know already we can write f of z as what? F of z we can write as sorry. So this, because we are using that, so don't confuse. So let's take this as some h of z. Okay. I hope we have not used h of z here. Okay. Then f of z we can write it as z minus z naught whole power m into g of z, where g of z is analytic at and non-zero at z naught. That is important, right? Therefore, what can you say about f dash of z? Simply apply this u times v method. Then we get this and divide by f of z. Whatever we get here is a simple calculation. Then what it says is that this g dash of z upon g of z, because g is non-zero at z naught, okay, so there is no problem. So it is analytic, g dash of z by g of z is analytic at z naught, okay. And because once a function is analytic at a point, then this g dash of z upon g of z has a Taylor series representation, okay, Taylor series representation. So about z naught, therefore we can write this one, and hence there is only one term, which is this m naught upon z minus z naught, which is the principal part of f dash of z, because f dash of z by f of z is equal to m naught upon z minus z naught. This g dash of z by g of z, you can write it this as summation, say call it bn, okay, z minus z naught whole power n. N is from 0 to infinity, right? So this doesn't involve any negative powers of z minus z naught. So what involves in principal part is only one term, namely m naught upon z minus z naught, right? So therefore, what can you say about this z naught? Because it involves only finitely many, exactly one term. So therefore, it is a pole, particularly a simple pole, right? So z naught is a simple pole of f dash of z by f of z. And what is residue? We know already the coefficient of 1 upon z minus z naught, which is m naught here. So we got, if something z naught is a 0 of order m naught, then z naught is a simple pole for the function f dash of z by f of z with residue m naught. Same way, if at all this f has a pole of order mp, see p is just to denote it is a pole, okay, of order mp, and here it is 0, we have denote by zeros, okay. So suppose if z naught is a pole of order m, or you can call it mp, then again we can use, how we can write our f of z as some phi of z upon z minus z naught whole power m, that, or you can this mp, okay. Or if you want to write it in the same format, you bring it in numerator, that is z minus z naught whole power minus mp into phi of z, okay. Now what we know about phi of z? Phi of z is analytic, okay, and non-zero at z naught. Therefore, it has a Taylor series representation. Then you multiply this, okay, and what you will have here is, we get that this z naught is a simple pole with residue minus mp. Whatever coefficient, that here m naught, and what you will get here is minus mp. That's all, okay. So you will have a if it is a simple pole, then residue is minus mp, and if it is a 0, then residue is m naught. That is what we have calculated here, right? Now therefore, by Cauchy residue theorem, these all become poles for this f dash of z by f of z. So 2 pi I times sum of the residues, okay, you can call it, say suppose they are finitely many, 1 to n, and these residues we can separate using zeros of f and poles of f. So this all belongs to poles of f, and this belongs to zeros of f, okay. So residue of f dash of z by f of z, where zk is a 0 of f and zk is a pole of f, right? Then what we will get here is, if it is a 0, then of whatever order you call it, m0 or mk, whatever, then this residue is simply sum of all those residues, right? Similarly here, this sum of the residues is nothing but sum of this mp, whatever minus mp we got, you will get here, right? So in this sum, what we have? In this sum, we have all m naught is the zero of its multiplicity, right? So what we are taking here is sum of all zeros including multiplicity, right? Those m naught are the how many times it is repeating, 0. Similarly, for pole, this mp denotes how many times that it is a pole of which order, right? So this summation m naught is nothing but with multiplicity number of zeros. Similarly, this mp, sum of mps, is nothing but number of poles, right? So what we have here is we got integration of c f dash of z upon f of z dz is 2 pi I times the difference of this z minus p. Okay, so if we can bring this here, that what we will get here is 1 by 2 pi I integration of f dash of z over f of z dz. This is simply z minus p. Okay, if you see this one here, if you consider this as 1, which is left hand side is winding number, right hand side is same, which is as this one, left hand side of this one, right? So therefore from 1 and 2, what we can observe is the winding number, value of winding number is 1 upon 2 pi I integration of f dash of z upon f of z dz, which is in terms of zeros and poles of the given function f is z minus. Okay, fine. Now we'll see one of the application of this argument principle. Okay, namely Rouches theorem. What it says is that, again, take C, denote a simple closed contour. Okay, and suppose that we have two functions f of z and g of z, which are analytic inside and on C. Okay, so we have some C and we have f and g, both are analytic inside. Okay, and suppose this f dominates, that means mod f of z is greater than mod g of z at each point on this z. So whatever points if you take, for all z belongs to C, then this, because it dominates, the zeros of this function f of z and f of z plus g of z, okay, for this both will have equal number or same zeros. These two functions have same zeros. Again, we are every time when we say zeros with counting multiplicity, okay, inside C. So what it says is that we can have some region where we can talk about the zeros of a analytic function. Okay, and remember, if this f can dominate on C, then zeros of f is same as zeros of this f of z plus g of z. That means this part is not going to play much role. So sometimes it is easy to find the zeros of f of z. Okay, so to understand this function, zeros of this function, we will try to see which part of this function, namely f of z, is dominating, okay, the remaining the dominating the f of z plus g of z on this C. Okay, so if you can have a function which can dominate, okay, fine. So this f of z and f of z plus g of z both will have same number of zeros, provided if f of z dominates this g of z, that means this condition, okay, on C. That means this g of z is not going to play much role while finding the zeros, right? The proof is not much difficult. Since f of z is strictly greater than g of z and mod g of z is greater than or equal to 0, so therefore what you will see here, mod f of z is also strictly greater than 0. So what we get here is mod f of z is also greater than 0, and mod f of z plus g of z. Okay, by using triangle inequality, what we get is, again, it is strictly greater than 0. Okay, so both, what you can see is that they don't have zeros on this C. Okay, because to apply the previous result, we require that they should be non-zero on that C, right? And if we denote this z of f, which is nothing but zeros of f and z f plus g, okay, which are nothing but zeros of this function, namely f plus g. Okay, then again, whenever we say, it always counting multiplicity is included. Okay, if something is repeated, say for example 1 is a root, okay, 3 times, then in number of zeros we are counting that 1 as 1 1 1 3 times. Okay, so therefore this f and f plus g both are analytic, it is already given here inside and on C, okay, they don't have poles. So in this result, the poles concept is gone. Only when you have this one, then 1 by 2 pi times argument of f of z is simply z, number of zeros. Okay, so for f of z, it is zf. For f plus g of z, it is zf plus g, because both are analytic inside, so we don't have any poles there, right? So what we got here is, therefore, if we combine these two, what we get is that zf, that means 1 by 2 pi this delta c argument of f of z, which is nothing but z minus p, where poles are 0, so this is zf. Similarly, 1 by 2 pi this argument of f plus g, okay, of z is zf plus g, right? That is what we have written here, because they both functions doesn't have poles. Okay, then we'll try to simplify this part, that is the change in argument of f of z plus g of z, because g of, you simply take out f of z common, because on C f of z and g of z both are non-zero, so I can take f of z outside, it is 1 plus g of z by f of z. Then by applying the fact of argument of product of 2, that means using the fact that argument of z1 z2 is argument of z1 plus argument of z2, right? This is same as, therefore the difference is same as difference of these two. Okay. Now to understand this, you call it this as capital F of z. So assume that this f of z is 1 plus g of z by f of z, right? Then of course this zeros of f plus g is 1 by 2 pi times argument of f of z plus 1 by 2 pi times this argument of this delta team. This we have call it as simply, this we have called it as simply capital F of z. So this is zeros of f plus g. Zeros of f plus g is 1 by 2 pi times of this value. So simply divide 1 by 2 pi to both of this. So 1 by 2 pi times the winding delta c of argument of f of z plus 1 by 2 pi times delta c of argument of f of z. See, what is our winding number when we started discussing here? So this is nothing but 1 by 2 pi, whatever we are calling it as winding number. So zeros of f plus g, sorry, here. So therefore zeros of f plus g is nothing but winding number of f, okay, plus winding number of this capital F, right? Now, what is this capital F of z? Argument of this capital F of z. If we observe this here, from this f of z minus 1, okay, this one is nothing but g of z by f of z. Okay, so if you take modulus, this is this. But we know by given assumption f of z is strictly greater than g of z. So therefore when you take modulus, this is strictly less than this, right? So mod f of z minus 1 is strictly less than 1. Therefore f of z cannot be 0. F of z cannot be 0, right? F of z cannot be 0. That shows that the whatever capital F of z we are having under the new transformation w is equal to capital F of z, this f of z is not at all 0 here, because it is strictly less than 1. That means what? The under the transformation w is equal to f of z, the image of C lies in the open disk mod w1 w minus 1 less than 1. Okay, so whatever we are taking here, it doesn't include 0. It is strictly, because if you call it this as w, then w minus 1 is less than 1. This transformation, right? So the whatever gamma we are talking, which is the image of this C under the transformation w is equal to capital F of z, then one can check that this gamma lies here, which is mod w minus 1 less than 1. Okay, then you can check that it doesn't involve, therefore this image does not enclose the origin w is equal to 0. Okay, because if you substitute 0 here, right, it is what are all points which satisfies this less than 1. Okay, that clearly doesn't include w. So if it doesn't include w, then winding number of this capital F of z is equal to 0, which we have started when we define winding number, we have shown that if at all it doesn't revolve around 0, then winding number is 0. Okay, which I have already explained, right? So therefore the winding number of this capital F of Z is 0. Okay, so therefore this part is not there. This is equal to 0. Hence Z of F plus G is equal to, so what we are getting here is Z of F plus G is same as Z of F. That means number of zeros of F is same as number of zeros of F plus G, right? Under what conditions? If mod F of Z is strictly greater than mod G of Z, F and G both are non-zero, okay, on C, and they should be analytic inside C, right? Let's quickly see an example how we can use this Rouches theorem. Many competitive exams, such results they will ask. So they simply ask, remember this result only says how many zeros are there. What zeros this result doesn't provide to calculate. Okay, you can only say that how many zeros it has. So if you take the example Z power 7, if you want to know number of roots of the equation Z power 7 minus 4Z cube plus Z minus 1 is equal to 0, inside the unit circle mod Z is equal to 1. So this is our circle, this is our C. So inside, how many zeros are there for this function? Z power 7 minus 4Z cube plus Z minus 1. Okay. Now the idea is we want to, this is your new function. Okay. So we want to identify something like F of Z from here. Okay. Such that this one we have to write it in the form of F of Z plus G of Z. So this is our is same as Z power 7 minus 4Z cube plus Z minus 1, such that mod F of Z value is strictly greater than mod G of Z on this C, which is mod Z is equal to 1. Then number of F zeros of F is same as zeros of G, number. Okay, number, again I am saying how many zeros it will have, number. We are not saying the roots are same. Okay, if at all whether I have written same number of zeros, we want to write here same number of zeros. Okay, not same zeros, same number of zeros. Fine. So how we can do this is not so difficult. One can easily check that which one dominates on mod Z is equal to 1. So simply take F of Z as minus, so you take F of Z as minus 4Z cube, then this value, this mod F of Z is always 4, and if you see mod G of Z, this is always less than or equal to 3 because mod Z value is 1, right? Okay, so therefore mod F of Z is strictly greater than mod G of Z, and we know F of Z is equal to 4Z cube. This has only one 0 with multiplicity 3, 0, 0, 0, right? So therefore this F has 3 zeros inside C. Therefore G of F of Z plus G of Z, which is this original one, also have 3 zeros inside C. Okay, so we can conclude that this F of Z plus G of Z also has 3 zeros inside C. Okay, as a application of this result, we can give second proof for fundamental theorem of algebra using this Rouches theorem. That means take P of Z, okay, which is A naught plus A1Z plus and so on EAN Z power n, where AN is non-zero. We want to show that this polynomial has exactly n roots, okay, with multiplicity. There is no problem. So we want to show that this polynomial has n zeros. So what is the idea? We will write this function as sum of two functions. Okay, one function dominates the other when you consider some curve. Okay, so that whatever roots it will have, this P of Z will also have same number of zeros. That is the idea. So what should be our guess? You take our F of Z as AN into Z power n, and G of Z is remaining. That means A naught up to AN minus 1, ZN minus 1. Okay, then we want to show that mod F of Z is greater than mod G of Z, okay, on some C, right? On some C. Clearly this F and G, they are polynomials, so they are analytic everywhere. Okay, so whatever curve we take inside that also they are analytic. So what we take here is take R greater than 1 radius and take the circle around 0, mod Z is equal to R. Okay, then what can you say about mod F of Z? Mod F of Z is mod AN into R power n. So mod F of Z, what we get here is mod AN into R power n. Then we want to find out what is modulus of g of z. So that one can easily apply triangle inequality, mod a naught, a1, r, and so on. Because r is greater than 1, then r square, okay, is less than r cube. R cube is less than r4 and so on. So every power here, we can replace this less than or equal to by one single one, which is r power n minus 1. That means here I can write that r power I is less than or equal to r power n minus 1 for all I starting from 1 up to even 0. You can write it here. So it is starting from 0 up to n minus 1. Okay, because r is greater than 1. That is the reason we have taken r greater than, right? Therefore, mod g of z, we can have everywhere here r power n minus 1 that we can take out here, and mod f of z is mod a n by r power n. Okay, so here r will come in denominator, and whatever coefficients you have this, you call it that as by some number. You call it some m or something. Okay, the idea is we want this is less than 1. When this will be less than 1? If r is bigger than, if r is bigger than this whatever we are having here, okay, if this much, if r is bigger than this, then obviously when you divide by r, you will get less than 1. Okay, r. What is another one? So here we want r greater than 1 also we require, and that whatever we are having, that should be bigger than this. So take r, whatever we are selecting r, it should be bigger than both 1 and this quantity. Okay, so if this quantity is already less than 1, then r greater than 1 is more than sufficient. If this quantity is more than bigger than 1, okay, then we want to make sure that r is bigger than this also. So if you take this, then we get that mod g of z by f of z is less than 1, right? So we can apply Rouches theorem. So if you apply Rouches theorem, f of z and f of z plus g of z, which is our given polynomial p of z, have both same number of zeros. Same number of zeros inside that r greater than 1, right? But we know n into z power n, it has n zeros with multiplicity. Okay, therefore p of z also has n zeros inside c. Okay, so again I repeat, this f of z and f of z plus g of z, we are only saying that they will have same number of zeros. We are not saying that they will have same zeros. That is completely wrong, right? So we have to keep that in mind whenever we are saying same zeros. So we are talking about same number of zeros. Okay, for example, this f of z has 0 0 0 n times, whereas f of z plus g of z, they will have some other zeros, but total number of zeros are here and here, total number is same. Okay, so you can have some exercise to explore this, how we can apply this Rouches theorem to calculate the number of zeros and so on. Okay, and here also this first example is about finding the winding number. Okay, and here the remaining two is about finding the number of zeros of the polynomial, and here mod z is equal to 1 and here mod z is equal to 2. Okay, so we'll stop here, and this concludes most of the properties of analytic functions. Okay, what is remaining in this syllabus is about transformation. Okay, Mobius transformation, or you can call it bilinear transformation, and some special functions. Okay, how some region will transform to some other region under some special functions. Okay, that we will see in next few more classes. Okay, we'll stop here. Thank you.